Okay, this one that I'm going to talk about is a work that I am doing in the last year in Padua with Simone Notarnicola and Mario Collura, and we try to build up a quantum simulator proposal for the study of an Abelian lattice gauge theory with a platform made up of Rydberg atoms. So I like to start from the very beginning because there is a very brilliant and intuitive idea of Richard Feynman, who said if we had to study a very quantum complicated problem that is inaccessible with other classical numerical simulation, a choice that we may try to do, is to get a quantum system which is more controllable with our possibilities, and try to do our best in order that the behavior of that system is as similar as possible to the one of our target problem, and so to understand a more difficult problem, studying a quite similar system, which, to be quite funny, is as intuitive as brilliant, but it is what we do since we are children. When we see real trains, we cannot have real trains, and we play with the smaller ones. Nowadays, quantum simulation is very widely applied for the study of condensed matter system. We can, for example, increase the dimensionality of system. We can implement artificial fields. Do not forget that the final goal is will be that of reaching some knowledge of a system, some property, which is not reachable within our simulation possibility. And a case in which this formalism has been largely applied is the one of the study of gauge theories, which, as we know, they are used to model the fundamental interaction in matter. We have, for example, the QED for positron and electrons, the QCD for the quarks. The key ingredient of this theory is imposing a set of local conservation law, which brings to the Gauss law, which bounds the gauge fields with the matter and gave rise to the interaction. And there are some phenomena, especially in the QCD and fermionic and study of fermionic matter, which are really difficult to study with the numerical simulation to the problems that rise up as the same problem. And to do as an example on which we focus in our scene, so for example, a key phenomenon in the QCD is the so-called string breaking. If we have a couple of a particle and then an antiparticle, the interaction between them is so strong that it's easier to create another couple to break the string between these two particles than keeping the two particles at a large distance. Studying QCD with quantum simulation is an attempt which has been tried for a long time, but so far with no handable results. Nevertheless, a lot of proposals has been made, and also some experiment has been recently done for the study of a Abelian lattice gauge theories. A lot of proposals are based on use of ultra cold atoms platforms, and for example, in a very recent experiment, a very small one-dimensional system has been studied with trapped ions in a lattice. Our goal is to show a setup for a quantum simulator which used a Rydberg-Atoms platform, as I will show later, then that can be used for the study of the real-time dynamics in a way that the size of the system can be naturally scaled to large sizes. So I will start from a brief review of the lattice gauge theory ingredients that I need for introduce the model that we consider. So the Hamiltonian that we consider is starts from the Schwinger Hamiltonian for the QED. So we have three terms. We have a mass term which is defined through fermionic operators that are defined on the sides of a one-dimensional lattice. Then we have the electric field energy term, and then the hopping term, which is responsible for the hopping of fermions from a site to another, and at the same time, it contains an operator which changes the value of the electric field in order to keep the local gauge constraint valid. Due to the so-called fermion doubling problem, we use the formalism of the staggered matter field, which means that we separate the even sites and the odd ones in the sense that a full even site represents the presence of an electron, while an empty odd site represents the presence of a positron. And in this way, the hopping of a particle from a site to another represents the creation of a positron and electron pair. Accordingly, we see that the value of the electric field change, passing in this case from 0 to 1, because we have a positive charge here and a negative one here. The electric field is a problem, let's say, when we want to implement a quantum simulator, because in the original Schwinger model, the spectrum of the electric field is continuous and unbounded up to infinite positive values. If we want to implement this field, this quantum field, with some artificial degrees of freedom, we need some trick. So we need to discretize its spectrum and to bound it. A very used formalism to do this operation was the quantum link models, in which this operator here and the electric field operators were replaced by spin operators. But in this way, this operator here should be a raising or lowering spin value, which is not unitary, while this operator must be unitary in the Hamiltonian. So the approach that we choose is to represent the electric field as a clock variable, which in our case takes three possible values. Choosing three possible values is important because in this way we have one eigenstate that we associate with a zero energy for the electric field, and two states which correspond to a non-vanishing energy. And this will be crucial for what we will see later. Then we have to impose the Gauss laws must be imposed, and the effect of the Gauss laws is to restrict the Hilbert space of the fermionic matter and the electric field to a certain set of state which satisfy the continuity law, according to which if there is no charge on a site, then then the electric field do not change from one link to another one, while instead, if we have a charge, for example, a negative one, the electric field will decrease, passing, in this example, from 1 to 0. This means that we can efficiently write a basis of the Hilbert space in which the Gauss law is satisfied, no longer by using both the matter and the gauge-built basis, but using one of the two bases and expressing all the operators and the other states as a function of the other field. In this way, our choice is to integrate out in this way the matter field, which means that we can rewrite the Hamiltonian by making disappearing, by replacing the operator which counts the matter on a certain site, which is an operator which depends on the difference of the value of the electric field between two nearest neighbor links. And accordingly, we must take care of the hopping operator, because this operator looks at the site, checking if there is or not a charge, in order to perform the hopping. These two operators, psi and psi-daga, are replaced by two projector operators, which checks the difference of the electric fields between nearest neighbor links and return a non-vanishing value only if there is an agreement between the required value of the charge and the difference of the electric field. I do not go into the details of the expression for these projector operators, but I have them if you are interested. But in any case, this Hamiltonian only lives on the Hilbert space of the electric field defined on the links of the lattice, and more importantly, it is still local. And this is something that if we would have integrated out the matter field and not the gauge one, this condition would not have been satisfied. So this is important to our formalism. So starting from this Hamiltonian, this is the one to which we want built on a quantum simulator, for which we use a platform of Rydberg atoms. Their importance is in the fact that they can trap it by some array of optical tweezers. The interaction between the atoms is highly controlled by their distances and the states to which they are excited, because we have these neutral atoms that can be both in their ground state or in an excited Rydberg state. They can be coupled by a Rabi frequency, and this term is represented here in the Hamiltonian. By a detuning, we can enhance or not the ground or a Rydberg state of each local site, and then we have the interactions which are provided by their dipole interactions, which in the case of S-type Rydberg states, they are anisotropic, as it has been shown in some experimental paper, and they depend as 1/6 power of their distances. And it is very important when we want to do a local constraint dynamics, as it is the case for our gauge theory, that, for example, we can forbid two atoms to be excited at the same time if they are too close, and this mechanism is called the Rydberg blockade mechanism. So we want to use this mechanism to implement the gauge constraints in the Hamiltonian that I've shown before. First of all, I have to show how the link can be represented, so each single link of the electric field. Since, as I told, we have 3 values for the electric field, we take 3 atoms, we arrange them in a triangular shape, and we assign to each state in which only one of the atoms is excited a value of the electric field. We have to take care of the fact that potentially this local Hilbert space has dimension 8, but we can prevent the occupation of the other states, for example, by taking the tuning, which prevents the absence of any excitation, and by setting the distance among them to be short enough to have that the Rydberg blockade prevents double excitation in the same link. Then we implement the electric field and energy by modulating a local detuning between associated to these 3 atoms in such a way that it is larger for the 2 atoms that we want to represent the non-vanishing value for the electric field, and 0 for the zero electric field energy. In this way, the local link dynamic, which means that the electric field changing, passing from -1, 0, and 1 according to the operator, is a second-order process in the excitation of the atoms, in which we pass from a state in which this atom is excited to some virtual states in which you have no excitation or to excitation, to a state in which another atom is excited. We'll see later the process expression, but it is a second-order process in the Rabi frequency omega. This is concerning the dynamics of the Singlelink. Now we want to consider the lattice structure and implement efficiently the Gauss law. In order to do this, we consider a link and we assign the values. We assign the values of the electric field to the excitation of this atom, and this atom respectively. The take-home message is this shape. And then we see that we set that the distance between parallel atoms must be short enough to have Rydberg blockade that prevents these two excitation along these distances, but not short enough to allow double excitation along the diagonal. And this is perfectly possible because the ratio between the interaction is of the order 1/10, which is enough to allow this mechanism to take place. So what do we do? Suppose that we have that between these 2 links, the charge that can sit is 0 or 1. So what we do? That if we start from this state and we have 0 charge, for example, the electric field can be 0 or 1 if it is increased, but cannot take the value -1 on these links here. And so we assign to the excitation of this atom this value for the electric field. And accordingly for the others, the state -1 cannot take the values, cannot correspond to a value 0 of the electric field in the successive link according to the Gauss law. And so the electric field here associated is 0, and so forth. So the association of these states to the excitation of these atoms is related to the possibility of spatially modulating the detuning of the excitation to the atoms, which is nevertheless something which is done in the experiment. And at the end of the day, by a second-order perturbation calculation, what we have is that the original Rydberg Hamiltonian, in which all possible excitation were allowed and all the interaction terms were considered, can be rewritten in this form, in which theta and theta prime means that theta is one of the three possible states in which one atom is excited. So we have a local part, which means that we pass from an excitation to another. The prime of the sum means that we are taking on only the allowed transition according to the Gauss law. And then we have a local energy term which assigns the energy to each excited atoms by time. Looking at the expression and the exact expression that we obtained for the hopping parameter, we see that there are some constraints which must be satisfied. In particular, delta is an overall the tuning which is applied to all the sites. V is the diagonal interaction, let's say, and VL is the interaction between these sites. So what we have done next, after obtaining this Hamiltonian, was to find some parameter regimes in terms of the interaction and the interatomic distances, which allowed a good comparison between the lattice gauge dynamics and the Rydberg one. And so, for example, this is what we have done. So I am showing here as a first example the dynamics of the bare vacuum. So we take as initial state the state in which the excited atoms reproduced the bare vacuum of the lattice theory, and we let it evolve, switching on the hopping between them. And so what we observe here we are showing both, first of all, the exact Z3 dynamics and the Rydberg one, and we see that there is a fair agreement between these two curves. Take into account that these oscillations are due to the fact that in theory there is a three-dimensional local Hilbert space, but in practice this Hilbert space is dimension 8, and this oscillation corresponds to the transition for forbidden states, to say. But then let's observe that if the ratio between the electric field energy and the hopping parameter is very high, there is a very strict correspondence between the Schwinger model, in which the electric field is not bounded, and our model, while this correspondence does not hold when we take a low ratio between the electric field energy and the T parameters, meaning that Z3 and thus our quantum simulator is a good approximates quite fairly the Schwinger QED model for large value of G. What we are considering here is the case in which the mass is 0, but there is also the possibility to modify the model, the quantum simulator, in order to also add a non-vanishing mass term. A more interesting case to study is the string dynamics, because in this way, in this case, due to the fact that we can actually control the ratio between the energy of the electric field and the hopping parameter, since, as I told before, our electric field can be both 0 or non-zero. This means that by changing this ratio, we can observe two very distinct dynamics. One in which an initial electric field string breaks during its dynamics, and one instead in which the string does not break. And this we think is somehow the strength of the novelty of our proposal. Since in other proposal the electric field was restricted only to two possible values, plus minus 1/2, for example, and so this ratio was meaningless because the electric field energy was a constant term, and so only a delocalized a string breaking dynamics was able to be observed, while we can tune this ratio and observe different dynamics. And this somehow is a phenomenon that has been mapped on some phenomena similar to those that happens in the QCD, which may make interesting to study some very well-known cases, the QED for more difficult model.
So are there any similarities between the string dynamics and the Z3 model?
What?
Are there any similarities
between
the string dynamics and the Z3 model?
Similarities with between this model and what?
Z3, the one you just explained before. Yeah.
This is the Z3,
Exactly.
and this is our quantum simulation results. Okay. Yes, these are the two evolution to show that the two phenomena, although the differences in the dynamics appear, are clearly distinguishable. A very last remark corresponds to the fact that here we see this change of the value of the electric field, which might be thought to be a sort of string breaking, and instead, if we compare the string dynamics of the Z3 model with that of the Schwinger model, we see a difference. But this is just due to the Z3 nature of our model. Due to the parity of the sites and the allowed value of the electric field, here the transition to positive values is just due to the oscillation from the most negative value to the most positive one, which is a feature of the Z3 model and not a string breaking effect. So I can conclude saying that we have implemented a quantum simulator model for a lattice gauge theory, which needs experimental platforms which are fully already available nowadays in experiments that have been done, that would allow to reach some considerable size of the system, since the simulation that I've shown use 20 sites, which will mean 60 atoms, which is of the order of the experiments that have been done nowadays. And there are some comparison which can be done between our quantum simulator dynamics and the Schwinger model, as well as the fact that we are able to see the transition between a confined string dynamics and the breaking string dynamics. The possibility of scaling the size of this system maybe will open the way to the implementation of some scattering pattern which are in principle realizable on our model. And I have concluded by thanking Simone Montangero and Mario Collura, for which I have worked for this project. Thank you.
So, for the comparison, like you want your hidden simulation to be predictive for the rest, and now for the real dynamics. Now you have those oscillations and you can explain those, so that's fine.
Yes.
But how can you reduce them? Because in the end, you want to have something which, you do not know how to simulate classically. So in the end, you will have some, you want to simulate some system which you cannot do classically,
Yes.
and you will get some behavior there. And then you want to know whether the oscillations that you get, they are physical or not. So then it becomes important whether you can suppress those oscillations to really make something which is predictive of the actual dynamics. So do you have ideas how you can suppress that and get closer to the actual curves?
Okay, yes, but the point to be stressed is this one, that due to the fact that a very naive way to suppress this oscillation, of course, is to make these distances as short as possible, but allowing the excitation along the diagonal. So there is a non-small set of constraints which must be taken into account to find a regime in which those oscillations are minimal. So with the setup that we consider, which use anisotropic interaction, that regime there is one of the cleanest that we have observed, actually. But and this is something that that can be improved with some more deep knowledge of other kinds of excited states, because maybe the unwanted excited states may be enhanced by using some not isotropic states, for which also the dipolar interaction may be exploited to enhance the Rieber blockade when desired, to say. I know that is a partial answer, because it has been not easy, actually, but what I say is that maybe it can be made cleaner, but I mean, there are models in which some clock variables is needed, and this might be a first proposal to implement them. And I will say that this kind of reasoning is a quite hot topic, I will say now, because also in the recent proposal for the 2D lattice gauge theories, it is all based on enhanced excitation and forbidden one, which is fully based on this geometrical scheme. So it's something on which there is some discussion to get the best improvement of it. Yes.
Could you comment on the Z-free setup where you have the clock Hilbert space for the electric field? So if I would think of the electric field, usually I couldn't switch from a high-end electric field to the opposite, right? So what's the relation to? Okay,
the point is that there are two, as I said, there are two. There is one mainstream way to truncate the spectrum of the electric field, which is the quantum link model, which simply says that there is no. I mean, this is the whole spectrum. I simply say that above this line there are no states. And when I am here and I would like to jump here, the state is annihilated. What I am saying is that the spectrum can be somehow deformed to a periodic function such that when I arrive to the end, I simply come back to the other state. Is unphysical. Is unphysical as we think, as we will compare it to our expectation, as you said, but maybe not less than the fact that you arrive at a certain point and you are simply annihilated. And moreover, there is a formal, more particular, which is the fact that, as I said, in the Hamiltonian, yes, this operator here is unitary in the original theory. This is the propagator of the vector potential. Is the exponential of Hermitian period. Sorry, I jumped too much. Okay. which is unitary. In the quantum link formalism, it is replaced by some S plus, S minus operator, which are not unitary. While in our theories, this unitarity is maintained. And moreover, as I showed in the very last plots, you can find some peculiar behavior due to the fact that you pass from the -1 to the 1 value and vice versa, but they do not affect, for example, the string breaking or confining dynamics. So yes, there is this difference which, comparing to an electric field, has not a direct physical meaning, but nevertheless it allows us to observe the characteristic of the dynamics that we would like to check.
But then the intuition is that if you have string breaking, then there's no high field such that you don't have this jump, or how would you explain that it doesn't play a role in the end effectively?
Because is a matter of the transition which are allowed within the engaging invariant states at the end of the day, and the difference is maybe I'm faster from here. Okay, here for example, I mean here the value of G is very high, so the value of the electric field is not coupled to the zero states. Okay, so you start from the value -1, and then apart from very slow fluctuation, you remain there. Here, instead, you might see, oh, look, I am going to 0, then to 1. But here, from an energetic point of view, you are not doing anything different from here, because this 0 here does not mean that you are in the 0 value of the electric field. You are in superposition of 1 and -1, because they have the same energy in your model. Okay, so and you observe this oscillation from an energetic point of view, and so from the string breaking point of view, you do not have a difference. And take into account that here you see it because you have just one non-negative value. If your spectrum will be higher, you will have I mean, if it would be larger, so you may have many different non-zero values for the electric field. You will observe your dynamics quite similar to the Schwinger one, apart from this transition that you would observe when you reach your spectrum, the border of your spectrum.
So if we had Zn, basically the Zn picture would converge to the Schwinger model? Or?
Yes.
And if you want to implement Zn instead of triangles, you would just do n-ones or something like this?
It is all a geometric matter of how you shape your lattice here. I have seen, for example, that with the 4, so Z4, you may do that because it is a different geometry. You have to put not aligned squared but rotated squares by 45 degrees, for example, and you see that also in this case you have two values of energy for you have the proper interaction, which represents the zero energy, the vacuum configuration, and the charged one, if you want. So in principle you can, but then becomes a matter of the geometry. And above 4, I don't know if it is possible, because the other point is that, imagine that you have a circle. In principle, you may put how many atoms you want, of course, But first, the distances but being always such that you have only one atom excited, which is difficult. And then you don't want that, that the transition between a state and any other of the states. An atom should go to the ground state, but only the nearest ones should be then excited. So this is more difficult to be implemented, yes.